Okay, let's jump right into this. It's the ultimate cosmic question, right? A thought experiment that completely obsesses physicists and sci-fi fans alike. What actually happens if you go into a black hole? We all know it's a cosmic point of no return, but the actual physical experience of crossing that threshold? Well, it defies literally almost every intuition we have about how reality works. In this explainer, we're going to trace the exact journey of a human observer plunging straight into the abyss. And I promise you, what awaits inside is far, far stranger than just being crushed in the dark. The absolute most fascinating thing about this whole journey is that the outcome depends entirely on who's watching. General relativity reveals this mind-bending duality. Basically, the math says that if you fall in, your fate is completely different from what the rest of the universe sees happening to you. You are simultaneously frozen in time and plummeting toward the end of it. So, how exactly is that even possible? To answer that, let's start with our first perspective, the distant observer's illusion. Imagine you're safely parked on a distant spaceship, watching a really brave friend take the plunge. To wrap our heads around what you'd see, we have to look at two distinct types of time. First, we have coordinate time, which is the time measured by a clock sitting with our distant observer, totally safe from extreme gravity. Then we have proper time. This is the time ticking normally on the actual wristwatch of the astronaut who is falling. Because gravity bends time just as severely as it bends space, as the astronaut gets closer to the event horizon, these two clocks fundamentally disagree with each other. Just take a look at how this plays out mathematically. The red trajectory represents the astronaut's position according to coordinate time, so the distant observer's view. Notice how as time marches on, that red path asymptotically flattens out right at that dotted line representing the event horizon. According to the distant universe, the falling astronaut takes literally an infinite amount of time to reach the edge. But look at the blue trajectory. That's proper time, the astronaut's own clock. That blue path plunges right through the dotted line and hits zero, the singularity, in a very short, very finite amount of time. So, a huge question here. Does the astronaut actually freeze at the edge? No. The freezing is just an optical and coordinate illusion. What's really happening is that gravity of the black hole is so immense, it struggles to let any light escape. As the astronaut approaches the horizon, the light they emit takes longer and longer to climb out of that deep gravity well. The light gets stretched into longer, redder wavelengths, a phenomenon known as gravitational redshift. To the distant observer, the astronaut will just appear to slow down, turn incredibly red, and then fade into absolute blackness almost instantly. You don't freeze, you just completely vanish from the universe's view. Moving on to part 2, surviving spaghettification. Okay, so the outside universe can't see us anymore. Switching over to the astronaut's perspective, the biggest physical threat we face on approach is spaghettification. This happens because of extreme gravitational tidal forces. Think about it. If you fall feet first toward a black hole, the gravitational pull on your feet is much stronger than the pull on your head, simply because your feet are physically closer to the center of mass. This sheer difference in gravity pulls you apart vertically, while at the exact same time compressing you horizontally. You would literally be stretched into a long, thin stream of subatomic plasma. Not a great way to go. But here is where our intuition totally fails us. If you compare different black hole masses, something completely counterintuitive pops up. You'd naturally think a bigger black hole is way more dangerous, right? Actually, scratch that. It's the exact opposite. If you approach a small, stellar mass black hole, like one just the mass of our sun, the tidal acceleration between your head and toes is a staggering 19.6 billion meters per second squared. You'd be ripped apart when you're still 1,600 kilometers away from the horizon. But check out what happens with the big ones. If you approach a supermassive black hole with 100 million solar masses, the gravity differential is only 0.000019 meters per second squared. Guys, that is less tidal force than you feel just standing on Earth. A supermassive black hole is perfectly safe to enter. In fact, if you chose the right black hole, your journey could actually be quite a scenic route. If you fell into the ultramassive black hole at the center of the M87 galaxy, the one famous for that first ever black hole photo, the tidal gradient is so unbelievably shallow that you'd cross the horizon in complete physical comfort. You could survive for approximately 11.8 hours inside the black hole before reaching the lethal core. Which brings us right to the edge in Section 3, crossing the event horizon. Assuming we've survived those tidal forces, we arrive at the most famous boundary in all of physics. But here's the catch. There is no physical wall. There's no signpost, no bump, no flashing neon lights. Locally, space-time at the event horizon is exactly like empty space anywhere else. You cross it completely smoothly, and in your local reference frame, you're crossing it at the speed of light relative to the horizon itself. You honestly wouldn't even know you passed the point of no return. Now, while you might not feel the bump, the math tells us some truly bizarre phenomena are happening exactly at this invisible boundary. For one, the light pouring in from the outside universe hits a redshift factor of exactly z equals 2. Furthermore, the horizon acts as a null surface, meaning light pointing outward is permanently trapped, effectively hovering in place or just being dragged inward. Because you are accelerating inward, your eyes are actually falling faster than the outgoing light rays trying to escape. The incredible result of all this? If you look down, you can still see your own feet. The light from your lower extremities can actually still travel up to reach your eyes during the descent. All right, section 4, the ultimate visual distortion. As we fall deeper inside, what actually happens when we look back out at the rest of the universe? Well, because you're accelerating to extreme speeds, 3 terrifying optical effects dominate your view. First up is Doppler boosting. The light in the direction you're falling gets compressed into shorter wavelengths. The space ahead of you becomes fiercely blue, white, and blindingly bright. Second is relativistic aberration. Because you're falling so fast, incoming light rays from the sides get deflected forward. The entire universe behind you literally appears to fold forward right into your field of view. And finally, the pinch. In the last milliseconds of your fall, the entire view of the outside universe compresses into a thin, ultra-bright band of high-energy X-rays, which pinches off into absolute darkness just before you hit the center. Which takes us to section 5, when space becomes time. We've reached the absolute climax of our journey, where space and time literally swap places. Let's say you're inside the event horizon. You're in a spaceship and you suddenly realize you've made a terrible mistake. You point your ship directly away from the center of the black hole and fire your rocket engines at maximum thrust to slow your descent. Intuition strongly says this should delay your death, right? But the math of general relativity says that firing your engines actually dooms you to die faster. Why in the world is that? To really understand this, we have to compare the 2 scenarios. Outside the horizon, you have freedom of movement in 3 spatial dimensions, but time drags you inevitably forward. You can't stop Tuesday from becoming Wednesday. But inside the horizon, the causal structure of spacetime undergoes a radical coordinate transformation. The radial direction, the path to the center, becomes time-like. It literally becomes the forward flow of time. The singularity at the center is no longer a physical place in space you are falling toward. It is a fixed, inevitable moment in your future timeline. Because the singularity is in your future, all directions effectively point down toward it. Any attempt to accelerate away from it is geometrically equivalent to attempting to travel backward in time, which we know is impossible. When you fire your rockets and accelerate, you invoke special relativity, which tells us that moving faster increases time dilation, thereby shortening your proper time. By struggling and accelerating, you're just decreasing the interval of your own existence. You literally only use up your remaining time faster. One of the physicists in our sources perfectly summarized this terrifying reality with this amazing quote. "The black hole is a time bomb. There's no central singularity waiting for you in space. It is simply waiting for you in time. You are riding a ticking clock, and every single action you take to fight it only makes that clock tick faster." But hey, before we accept ultimate destruction, let's explore one final theoretical twist. What if our understanding of the singularity is actually incomplete? What if that crushing infinite density isn't actually the end of the road? This leads us to a fascinating concept called the quantum bounce. See, some cutting-edge quantum gravity models suggest that matter simply cannot be compressed infinitely. Instead of a singularity, the core of a black hole might actually be a highly compressed Planck star. Once it reaches maximum density, it experiences a quantum bounce, turning into a white hole, which is basically the time-reversed equivalent of a black hole that ejects matter. Because of extreme time dilation, this bounce takes milliseconds for the core, but billions of years for the outside universe. So the ultimate takeaway here? If you fall into a black hole, you might not just be erased. You might fall right through the horizon, pass through the bouncing core, and be ejected into the far distant future of the universe, with all your quantum information perfectly preserved. A cosmic time machine, totally disguised as the ultimate void. And with that mind-blowing thought, I'll leave you to wonder, what exactly is waiting for us on the other side?